Journey to the edge of everything. The distances of space are unimaginable. Our minds weren't built to comprehend the vast, frozen emptiness between the stars. Yet right now, as you're watching this, humanity's most distant ambassadors are hurtling through the cosmic void, carrying messages from Earth into the eternal night. They've been traveling for nearly half a century, and they're only just beginning their true journey. Let me take you on a voyage unlike any other. From the loneliest machines humanity has ever built, to worlds that could harbor alien life, to galaxies so strange they challenge everything we thought we knew about the universe. And perhaps, if we venture far enough, we might finally answer one of humanity's oldest questions. Where is the center of it all? Our story begins at the edge of the solar system, where 4 spacecraft drift through the darkness, the loneliest machines in existence. Picture this: September 5th, 1977. A Titan Centaur rocket roars into the Florida sky, carrying a golden-plated spacecraft, no bigger than a small car. Its name is Voyager 1, and its mission is to visit Jupiter and Saturn. But that's not the remarkable part. The remarkable part is that 48 years later, it's still out there, 154 astronomical units from Earth, traveling at 61,000 kilometers per hour, so far away that radio signals take over 22 hours to reach it. Voyager 1 is humanity's most distant creation. Right now, it's crossing a region of space that no human-made object has ever touched before. The scattered disk beyond the heliopause, where the sun's protective bubble finally gives way to true interstellar space. The spacecraft is heading toward a hypothetical shell of icy objects called the Oort cloud. But here's the staggering part. It won't reach the inner edge for another 300 years. And crossing it entirely? That will take 30,000 years. Think about that for a moment. The pyramids of Giza are only 4,500 years old. The entire span of recorded human history would fit 6 times over in the time it takes Voyager 1 to cross the Oort cloud. But Voyager 1 didn't leave alone. 20 days earlier, on August 20th, 1977, its twin brother Voyager 2 launched first. Yes, you read that right. Voyager 2 launched before Voyager 1. The mission planners gave it a slower, more scenic route through the outer solar system. And what a journey it was. While Voyager 1 focused on Jupiter and Saturn, Voyager 2 became the only spacecraft in history to visit all 4 gas giants: Jupiter, Saturn, Uranus, and Neptune. At Jupiter, it photographed Europa's cracked ice surface, hinting at the ocean beneath. At Saturn, it measured the temperature of the atmosphere and discovered new moons hiding in the rings. But the real treasures came at Uranus and Neptune. When Voyager 2 arrived at Uranus in 1986, scientists expected a quiet, boring ice giant. Instead, they found a world knocked on its side, rotating like a barrel, surrounded by 17 previously unknown moons and a complex system of rings. 3 years later, at Neptune, the spacecraft photographed winds screaming across the planet at 2,100 kilometers per hour, the fastest in the solar system, and discovered geysers of liquid nitrogen erupting from the moon Triton. Neptune's gravity gave Voyager 2 one final push, flinging it out of the solar system's orbital plane at 15.37 kilometers per second. It will never approach another planet again. In 42,000 years, it will pass within 1.7 light years of a dim red dwarf called Ross 248. And in roughly 300,000 years from now, long after our civilization has either spread to the stars or vanished entirely, Voyager 2 will silently drift past Sirius, the brightest star in our night sky, at a distance of 4.3 light-years. But by then, no one will be listening. The plutonium power sources aboard both Voyagers are already fading. By 2025, the radioisotope thermoelectric generators will produce too little electricity to power even a single instrument. One by one, the systems will shut down, the transmitters will fall silent, and humanity's first interstellar ambassadors will become ghost ships, drifting through the galactic night for billions of years. Before Voyager 1 goes dark, though, it has one more gift to give us: data from the boundary, where our sun's influence ends. The heliopause isn't just an invisible line in space. It's a roiling, turbulent region where charged particles from the sun collide with the interstellar medium, creating complex structures of plasma and magnetic fields that we're only beginning to understand. Voyager 1 is sending back measurements from this alien frontier, teaching us about processes that occur throughout the galaxy. And then there's the newest member of humanity's deep space fleet, New Horizons. Launched in 2006, this piano-sized probe is the fastest object humanity has ever sent into space. After using Jupiter's gravity to slingshot itself to unprecedented speeds, New Horizons rocketed toward the outer solar system at 14 kilometers per second, fast enough to reach the moon from Earth in just 9 hours. On July 14, 2015, New Horizons gave humanity its first close-up look at Pluto. And what we saw shocked everyone. Instead of a dead, cratered ice ball, Pluto revealed itself as a geological wonderland. Nitrogen glaciers flowing across ancient water ice bedrock, mountains made of frozen water rising 3,500 meters high, a vast, heart-shaped plain suggesting recent geological activity. Pluto was alive in ways we never imagined. But New Horizons didn't stop there. It continued deeper into the Kuiper Belt, photographing the distant objects Quaoar and Arakoth, primordial remnants from the solar system's birth that have barely changed in 4.6 billion years. From this incredible distance, the spacecraft even measured the positions of nearby stars, like Proxima Centauri, seeing them from angles no human has ever seen before. Yet even New Horizons' incredible journey is temporary. Starting in 2026, its power supply will begin to fail. By 2038, at 100 astronomical units from the Sun, it will join its older cousins in eternal silence, coasting forever into the void. But here's the haunting question no one talks about. What will happen to these spacecraft in the deep future? Maybe they'll be vaporized by a collision with some dark asteroid we'll never know about. Perhaps our descendants, having mastered interstellar travel, will retrieve them and place them in museums. But most likely, they'll drift for millions of years through absolute emptiness, while cosmic rays and micrometeorites slowly tear them apart, atom by atom, until nothing remains but dissociated particles lost forever in the cosmic ocean. These machines are humanity's first footsteps into a universe so vast that our entire solar system is barely a grain of sand on an endless beach. So let's take the next step in our journey. Let's travel to the nearest stars and see what strange worlds await us there. The neighborhood. Stars. Closer than you think. When we look up at the night sky, the stars seem eternal and unchanging, but they're not. They're moving, racing through space at hundreds of kilometers per second, following ancient gravitational currents through the galaxy. And some of them are heading straight for us. 6 light-years from Earth, there's a small red star called Barnard's Star. You can't see it without a telescope. It's barely visible even with professional equipment. But this unremarkable little star has a secret. It's the fastest moving star in the night sky. It's traveling toward us at 106 kilometers per second, and in just 10,000 years, a blink of an eye in cosmic terms, it will become our closest stellar neighbor at just 3.8 light-years away. Barnard's star is tiny, cold, and dim. Its surface temperature is only 2,860 degrees Celsius, cool enough that it glows a dull red. It produces only 0.04%, as much light as our sun. But here's what makes it fascinating. It's ancient, over 10 billion years old, making it one of the oldest stars in our galaxy. It was already middle-aged when Earth was forming. And it might have a planet. In 2018, after 20 years of painstaking observations, astronomers announced evidence for a super-Earth orbiting Barnard's star. The planet, called Barnard's star B, is at least 3.2 times Earth's mass and orbits its star once every 233 days. It receives 50 times less energy than Earth gets from the sun, giving it a surface temperature around minus 168 degrees Celsius. You'd think that makes it lifeless. But here's where it gets interesting. The planet is massive enough that its interior could be heated by tidal forces and radioactive decay. Beneath a frozen surface, there might be a liquid ocean kept warm by the planet's own internal heat. And if there's liquid water, there could be life, simple perhaps, thriving in the darkness like the creatures around Earth's hydrothermal vents. If life exists on Barnard's star B, it's had plenty of time to evolve. 10 billion years is more than twice the age of Earth. Who knows what might have developed in all that time? Now let's jump 13 light-years from Earth to a star system that might be one of the most important discoveries in the search for alien life, Wolf 1061. This red dwarf star is utterly unremarkable, small, cool, dim, one of hundreds of billions like it. But circling this star are 3 rocky planets, and one of them sits right in the middle of the habitable zone. Wolf 1061c is a super-Earth, about 3 to 4 times our planet's mass, with 60% higher gravity. It receives less energy from its star than Earth does from the sun, giving it an average temperature around minus 50 degrees Celsius. Cold, right? But wait, that's the equilibrium temperature, what the planet would be without an atmosphere. Add in greenhouse gases, and the temperature could rise significantly. Here's what makes Wolf 1061c special. It's far enough from its star that it probably isn't tidally locked. It has days and nights, seasons, weather patterns that distribute heat around the planet. If it has oceans, and that higher gravity suggests it might, they could be vast, covering most of the surface, warmed by a thick atmosphere, and it's the 5th closest potentially habitable world we've found. Close enough that future telescopes might be able to study its atmosphere in detail, looking for chemical signatures of life. But before we get too excited about finding aliens, we need to talk about the incredible machine that's revolutionizing our understanding of distant worlds. The Eye That Sees Through Time. On December 25th, 2021, Christmas morning, a European Ariane 5 rocket lifted off from French Guiana, carrying the most ambitious space telescope ever built. It took 25 years to design and construct. Its mirror is so large it had to fold up like origami to fit inside the rocket, and it's so sensitive that it can detect the heat signature of a bumblebee on the moon. The James Webb Space Telescope is not just an observatory. It's a time machine. Webb doesn't orbit Earth. Instead, it sits 1.5 million kilometers away at a point called L2, the second Lagrange point, where Earth's gravity and the sun's gravity balance perfectly. There, hidden behind a tennis court-sized sunshield that keeps its instruments at minus 233 degrees Celsius, Webb stares into the deepest darkness of space, collecting ancient infrared light from the universe's first stars, and it's already rewriting astronomy textbooks. Take the case of WASP in 96b, a gas giant planet orbiting a star 1,120 light-years away. This planet is strange. It's almost as big as Jupiter, but only half as dense, like a cosmic marshmallow. It orbits its star once every 3.5 days, so close that its atmosphere is heated to over 1,000 degrees Celsius. In 2018, observations suggested WASP 96b had an impossibly clear atmosphere, the clearest ever seen on a gas giant. You could see straight down to incredible depths. Astronomers were thrilled. Here was a chance to study a planet's atmosphere layer by layer. Then Webb took a look. Webb's data showed something completely different. Clouds. Thick clouds of water vapor. The planet's atmosphere wasn't clear at all. It was opaque, filled with complex chemistry we couldn't see before. So, which observation is correct? We don't know. Maybe the earlier data was wrong. Maybe the planet's atmosphere changed. Or maybe, and this is the exciting possibility, we're missing something fundamental about how hot Jupiter atmospheres work. WASP 96b is now one of the most studied planets outside our solar system, and it's still keeping its secrets. But Webb's most mind-bending discoveries aren't planets. They're galaxies, 4 billion light-years from Earth. There's a massive cluster of galaxies called SMA CS0723. This cluster is so massive, containing the mass of trillions of suns, that it warps space-time itself. Light from galaxies behind it gets bent and stretched and magnified by the cluster's gravity, creating a natural telescope called gravitational lensing. When Webb pointed at SMA CS0723, it saw something extraordinary. A single galaxy whose light had been lensed not once, not twice, but 3 times, appearing in 3 different locations in the image. And because of that gravitational magnification, the galaxy's light was amplified about 20 times. Without that boost, we could never have seen this galaxy. It's so old and distant that its light has been traveling toward us for over 13 billion years. We're seeing it as it appeared just 200 to 700 million years after the Big Bang, when the universe was still an infant. And here's the problem. This galaxy is too complex. It shows structure that should take billions of years to form, but the universe wasn't old enough for that when this galaxy existed. Either our models of galaxy formation are wrong, or the universe is older than we think, or something very strange happened in the early cosmos. Webb is finding dozens of these ancient, impossible galaxies. Each one is a mystery. Each one challenges what we thought we knew. Worlds of water, worlds of fire. 42. Light-years from Earth, orbiting a small red star. There's a planet that shouldn't exist. At least, not in the form it does. Gliese 1214b is a super-Earth. 2.6 times our planet's radius, but only 6.5 times its mass. Do the math, and you get a density of just 1,870 kilograms per cubic meter, barely denser than water. In fact, calculations suggest this planet is about 75% water and ice, with only 25% rock and metal. It's an ocean world, but not like Earth. Gliese 1214b orbits its star once every 36 hours at a distance of just 2 million kilometers. That's 14 times closer than Mercury is to the Sun. The planet's surface temperature ranges from 120 to 280 degrees Celsius, depending on how reflective it is. At that temperature, with atmospheric pressure 15 times Earth's, The boundary between ocean and atmosphere blurs into something we have no words for, a transition zone where supercritical water exists in a state between liquid and gas. Descend through this hellish steam bath, and the pressure keeps rising. At around 100 kilometers depth, the pressure becomes so intense that water can no longer remain liquid, even at those scorching temperatures. Instead, it transforms into exotic forms of ice, Ice 7, Ice 10, that are denser than liquid water and sink to the bottom, forming an ice layer that could be 5,000 kilometers thick. Beneath that frozen ocean floor lies the rocky core, a world within a world, pressed under unimaginable weight, forever hidden from view. Could life exist in Gliese 1214b's ocean? Probably not. The water is too pure, too depleted in the minerals and chemical variety that life needs. But the sheer alienness of this world is staggering. An ocean hundreds of kilometers deep, transitioning from steam to exotic ices, all under crushing pressure and searing heat. It's a reminder that planets can be far stranger than anything in science fiction, and we think there might be billions of these ocean worlds in our galaxy alone. But not all potentially habitable planets are water worlds. Some are almost exactly like Earth. 101 light-years away, a red dwarf called TOI, 700 hosts at least 3 planets. The third planet, TOI 700d, is special. It's only 20 to 30% larger than Earth. Its mass is somewhere between 1 and 3 Earth masses. It orbits in its star's habitable zone, receiving 86% of the energy Earth gets from the Sun. And crucially, its orbital period is 37.4 days, long enough that it might not be tidally locked, meaning it could have day-night cycles. TOI 700d was the first Earth-sized planet found in a habitable zone by NASA's TESS Space Telescope, and it represents something profound. Proof that Earth-like planets orbiting in temperate zones are common. They're out there by the billions. If TOI 700d has an atmosphere like Earth's, its average temperature would be around -4 degrees Celsius. But add some greenhouse gases, which any planet with liquid water would have, and you could easily push temperatures into the comfortable range. There could be continents, oceans, clouds, rain, seasons. Could there be life? We have no way of knowing yet, but the James Webb Space Telescope is scheduled to study TOI 700d's atmosphere. We might, within our lifetimes, detect biosignature gases, oxygen, methane in the wrong proportions, chemicals that can only be produced by living things. Imagine that moment. The first confirmed detection of life beyond Earth. Not microbes on Mars or in Europa's ocean, but life on another world, orbiting another star, evolving under an alien sun. It would be the most important discovery in human history. Galaxies at the edge of madness. If you think planets can be strange, wait until you see what galaxies can do. 52 million light-years from Earth, in the Virgo cluster, there's a galaxy called M86 that's doing something almost no other galaxy does. It's moving toward us. Most galaxies show redshift. Their light stretched to redder wavelengths by the expansion of space. But M86 shows blue shift. It's approaching at 244 kilometers per second, and it's leaving a trail of destruction in its wake. As M86 barrels through the sparse gas between galaxies, it's like a ship plowing through water, except the water is million-degree plasma, and the ship is a collection of 100 billion stars. The collision strips gas from M86, creating enormous streamers of glowing hydrogen that stretch for hundreds of thousands of light-years behind it. Several of these gas filaments connect M86 to another galaxy, NGC 4438, that looks like it's been through a cosmic meat grinder. Astronomers think these two galaxies collided millions of years ago, with M86 tearing NGC 4438 to pieces. And this isn't the first time M86 has devoured a neighbor. Its halo contains the ghostly remains of dozens of smaller galaxies it absorbed long ago. But M86 isn't even the strangest collision victim. 227 million light-years away, there's a galaxy that looks like a jellyfish. ESO 137-001 is plunging toward the center of galaxy cluster A3627 at nearly 2,000 kilometers per second. At that speed, the intergalactic gas isn't just stripping away ESO 137-001's gas. It's being torn out in enormous tentacles that trail behind the galaxy for 260,000 light-years. And here's the surreal part. Stars are forming in those tentacles. Young, massive, blue stars are being born in the streamers of gas being ripped away from their parent galaxy, like seeds scattered from a dandelion in a hurricane. These stars will never know the galaxy that birthed them. They'll spend their entire lives in intergalactic space, orphaned in the void. Then there's the baby boom galaxy. We see it as it was 12.2 billion years ago, when the universe was barely 1.5 billion years old, and it's giving birth to about 4,000 stars per year, one new star every 2 hours. That's 400 times the Milky Way's star formation rate. Why is this galaxy in such a frenzy of creation? We don't know. Maybe it's consuming enormous amounts of gas from its surroundings. Maybe it recently merged with another galaxy. Or maybe this is just what galaxies were like in the early universe. Violent, productive, burning through their fuel at impossible rates. Watching the baby boom galaxy is like watching a time-lapse of cosmic evolution. We're seeing processes that shaped the universe in its infancy. Processes that no longer occur today. And finally, there's the Black Eye Galaxy, M64, 17 million light-years away. At first glance, it looks normal. A spiral galaxy with a dark dust lane across its center, hence the name. But when astronomers measured how it rotates, they discovered something impossible. The inner disk rotates one direction. The outer disk rotates the opposite direction. This shouldn't happen. Stars and gas in a galaxy should all orbit the same way, like planets around a star. The only explanation is that M64 is actually two galaxies, one small, one large, that collided billions of years ago at just the right angle and speed to create this bizarre counter-rotating structure. And somehow, miraculously, both rotation patterns survived. M64 is a frozen moment of cosmic violence, a collision captured in slow motion. The question that has no answer. We've traveled so far now, from the edge of our solar system to the edge of the observable universe. We've seen spacecraft drifting into forever, planets of steam and exotic ice, galaxies tearing each other apart across millions of light years. But now I want to ask you a question that might seem simple, but leads to the deepest mysteries of existence. Where is the center of the universe? It's a natural question. The solar system has a center, the sun. The Milky Way has a center, a supermassive black hole. Galaxy clusters have centers. Even superclusters have centers of mass. So, the universe must have a center too, right? Here's the strange truth. It doesn't. At least, not in any way we can point to. Let me explain. When we look at the universe on the largest scales, hundreds of millions of light years. It looks almost the same in every direction. Galaxies cluster into groups. Groups form superclusters. Superclusters form enormous filaments surrounding vast empty voids. This cosmic web structure appears roughly the same everywhere we look. There's no edge, no center, no special location. This is called the cosmological principle. The universe is homogeneous and isotropic. Anywhere you stand becomes the center of your observable universe. But wait, you might say, didn't the universe begin with the Big Bang? Shouldn't there be a point where the explosion happened? This is where our intuitions betray us. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Every point in space was there at the beginning, infinitely compressed. When the universe began expanding, it expanded everywhere at once. There is no location where the Big Bang happened because it happened everywhere simultaneously. Imagine the surface of a balloon with dots drawn on it representing galaxies. As you inflate the balloon, all the dots move away from each other. From any dot's perspective, all other dots are receding, and that dot appears to be at the center of the expansion. But there is no center on the balloon's surface. Every point is equivalent. Now add a dimension. Our universe is the 3D equivalent of that 2D balloon surface, expanding into higher dimensional space we can't perceive or point to. This expansion creates something called the cosmological event horizon. Because space itself is expanding, distant objects recede from us faster than light can travel, not because they're moving through space faster than light, but because the space between us and them is growing. Beyond a certain distance, currently about 46 billion light years, we can never receive signals from objects, even in principle. They've crossed our event horizon. And here's the haunting part. Every location in the universe has its own event horizon. Every observer sees themselves at the center of their own observable universe. There are galaxies we'll never see, events we'll never know about, entire civilizations that might exist beyond our horizon, forever hidden from us. The cosmic microwave background, the afterglow of the Big Bang, should help us find a center, right? This radiation comes from every direction in space at a temperature of 2.7 Kelvin. It's the oldest light in the universe, released when the cosmos was just 380,000 years old. For decades, we thought the CMB was perfectly smooth and uniform, but modern telescopes revealed tiny temperature fluctuations, regions slightly warmer or cooler by millionths of a degree. These fluctuations are the seeds that grew into galaxies. Scientists hoped these patterns might reveal a preferred direction, an axis of rotation, a center, but they don't. The fluctuations appear random, following statistical patterns predicted by quantum mechanics in the early universe. There's no arrow pointing to center this way. Some researchers have claimed to find anomalies, a dark flow of galaxy clusters moving in unexpected ways, an axis of evil in the CMB temperature map, mysterious cold spots that might be the signatures of other universes colliding with ours. But these claims remain controversial, and none provides evidence for a universal center. So here we are, standing on a planet orbiting a star in a galaxy that's one of hundreds of billions in the observable universe. We're 13.8 billion years downstream from the moment of creation, watching distant galaxies race away from us in all directions as space itself expands. And we might be nowhere special at all. Or, and this is equally valid, we might be at the exact center of everything, just like everywhere else. The universe doesn't have a center, because every point is the center. Or perhaps more accurately, the concept of a center doesn't apply to the universe in any meaningful way. We're asking a question that the cosmos can't answer, not because we lack information, but because the question itself might not make sense. And maybe that's okay. Maybe the universe is stranger and more wonderful than our human need for centers and edges and boundaries can accommodate. The eternal mystery. Our journey today has taken us from humanity's loneliest machines, drifting into the cosmic ocean, to the very edge of observable space and time. We've visited worlds of water and fire, watched galaxies tear each other apart, and confronted the unsettling possibility that the universe has no center, or that everywhere is the center. Every day, telescopes bring us new knowledge, new mysteries, new questions we didn't know to ask. The James Webb Space Telescope is just beginning its mission. The next generation of exoplanet hunters will launch soon. And somewhere out there, perhaps around a star we haven't even discovered yet, there might be someone looking back at us, asking the same questions. The universe contains billions upon billions of remarkable worlds, each one unique, each one a story waiting to be told. We could spend eternity exploring, and we'd never run out of wonders. Will we one day see the universe in its entirety? Will we unlock its deepest secrets? Will we find life among the stars? Only time will tell. But I know this: the journey itself, the asking, the wondering, the reaching toward the unreachable, that is what makes us human. We are the universe trying to understand itself. And that might be the greatest mystery of all. Thank you for joining me on this voyage. Until next time, keep looking.